Okay, so thank you. I would like to thank the organizer, but I think we should all thank the organizer. And the reason why that this has been a pretty nice conference, and I think the main idea of the organizer, which, if I am correct, is are Martin Bridgeman, Dick Canary, Fanny Cassel, Beatrice Pozzetti, and
I just told you.
Yeah, you just told me, but that explains you. I can't say it.
And Jean-François Quin.
Jean-Françoa Quin, of course. So the main idea of the conference was to bring two crowds together. I mean, people with background in let's say, geometry group theory, hyperbolic geometry, and people from the homogeneous dynamics. And this has been very successful at that. So we should really thank those people. It was very informative. So maybe I should do something about my iPad going to sleep. Anyway, so I'm going to start to talk about gauss polygons, Poisson brackets, and convexity. And to be fair, the title is on purpose not very clear, and we'll try to explain what I'm going to talk about. So let's start with some generality, and the first thing is when we consider a finitely presented group, or finitely generated is enough actually, and we consider some algebraic group, let's say some linear group defined by some equation, and we consider the space of representation of gamma into G, which is just a space of homomorphism up to conjugacy. This is an algebraic variety. Okay, so what is important here is that actually it's not the set itself, but what is important is the set of functions on it. And this object is totally defined by this set of functions. And this set of functions are the so-called oops.
Could you increase the brightness, please?
I cannot. Sorry. And okay. So what have I done? Ah, there it is. I'm sorry, I cannot. I've done this stupid thing of writing notes on a black background, and it's not a good idea on a projector. So you will have to bear with that. I'm really sorry. So what is important is a set of functions, and it turns out that this set of functions are also called characters. So what is a character? So a character is given by an element in the group. Okay. It's also given by a linear representation of your group G into some SL of V. And the character is just a trace of the image of lambda, of rho, of gamma. Okay, so that's the function of rho. Is this any better? Yes. I'm really sorry. This is I should have tested that yesterday, but for some reason it didn't work. So right, so what is important here is that you have a set of functions, which are these regular functions, and you define your variety by this set of functions. Okay?
And you say it's generated as polynomial algebra, actually even as a vector space, right? Or are these even a basis of the...
Right. No, I consider this as a polynomial algebra generated by...
Aren't these guys even a basis over the ground field?
Maybe, I don't know. I don't want to go into this. I just want to say that for character varieties, you have nice set of functions, which is a set of regular functions, and everything is built from that. So, right. So now another piece of information, something that you may know, is that if you have a symplectic manifold, you have a certain object which is called a bracket of a function. So how is it defined? Given a function, you want to consider it's a Hamiltonian flow. So it's a flow which is generated by this vector field. And this vector field, which is called xf here, is given by the symplectic gradient of df. So what is nice with symplectic manifold, to summarize, is that you have, given a function, you have lots of flow, lots of dynamics on your manifold. So, and then the Poisson bracket is given by the following formula. So you just take you take two functions, you take the two Hamiltonian vector fields, and you take the the symplectic value of these two Hamiltonian vector fields. So if you don't like this enough, there is another way to think about that. That's what is Fg? Maybe white would be better. What is Fg? You can see it as the derivative at time 0 of f composed with phi t, where this is the Hamiltonian flow of f. Okay? So I should say something. So it's, maybe that's your question. There is maybe the minus signs or whatnot of g. Of g. Thank you. So I thought it was the other question. The other question was that I got the sign wrong. So I should say that the whole lecture is under the random sign convention. And you shouldn't believe any sign which is in this lecture. But hopefully the signs in the paper are correct. So actually for the Hamiltonian there is two conventions. And Martin and I did not agree on which one we should use. And I don't even know which one I use. Okay, so now here is another fact, which is important. If you have a closed surface group, pi 1 of S, then the character variety admits a symplectic structure, which is called the Atiyah-Bott-Goldman symplectic structure. And then you have a Poisson bracket. And this Poisson bracket plays very nicely with the characters. And you have this beautiful theorem by Goldman. So what does this theorem say? If you take the Poisson bracket of two characters, that it is itself a character, but on a new, for new curves which are built from gamma 0 and gamma 1. So that's really a beautiful result. And that's one of the background of the subject I'm going to talk about.
What's the reference of the paper?
Which paper? Goldman?
No.
Oh, it's going. Let's say July 2023. Right. So.
Say it again. The Poisson bracket is again a character, but for a different curve.
Yeah, that's a beautiful result. Yeah. Wow. So. Right, so why do we care about Anosov representation? Why do I care? Because they are very flexible. They form an open set in the character variety. But it turned out there are way more functions defined on the moduli space of Anosov functions than just regular functions. So that's very important. And did I say that it was it was written, all that is a joint work with Martin Bridgeman, who is an organizer. This is why I whistled in this as a speaker. And so we are going to give you explicit formula of how to compute the Poisson bracket of these very specific functions that I'm going to describe. And we are going to use that to obtain convexity properties of the length functions. And all that will be using this combinatorial trick, which we call the Gauss polygon. I will also show you some application, not a complete proof, unfortunately, which is a proof of Potry-Sambarino result of the entropy being 1 on a Hitchin component without using even the definition of the entropy. So let's start. So the paper is really about general Anosov representation, but let's be simple and let's just consider projective Anosov representations. So since you have been here all week, You all know about what is an Anosov representation. So we start with a hyperbolic group, for instance, the surface group in our case. You have this boundary at infinity. So actually, in our case, it's S1. And I'm going to use a fantastic notation. I'm going to call the space of geodesics G. So in my talk, G is not going to be a semi-simple algebraic group. And G is just a space of geodesic. So what is a geodesic? It's just a pair of points, a pair of distinct points in the boundary at infinity. I'm going to use this notation. Right, so here's a little drawing of how do I feel about a geodesic. Okay. So projective Anosov representations are associated to the projective space. This means that you have limit maps, which are Hölder maps, from the boundary at infinity to the projective space, or to the dual projective space. So I'm going to use a slightly different point of view, just for convenience. I'm going to see that an Anosov representation has an assignment which associates to every geodesic, which is a pair of points, a projector, which is an endomorphism of my vector space. So what is this projector? You just take the projection on the line which is the limit parallel to the hyperplane which is defined by the starting point. Okay, so for me, an Anosov representation will be a map from the space of geodesics to the space, the endomorphisms. Okay. So let's explain some functions that you can get. So the first kind of function that you can get is the one that you heard a lot about, which are length functions. So in that context, you can consider, for instance, the length function of a closed geodesic, of a closed orbit of your flow, of an element of your group. And this is just going to be the logarithm of the top eigenvalue of your element gamma that you see as an element in the group. Okay, so that's being projective. For every element in the group, you have a top eigenvalues and just take the log of that. And that's what I called the length function, that everybody calls the length function. And this sort of has a flavor of characters, but you are taking the eigenvalues, not really an algebraic function, and then you are taking logs. So, and furthermore, what you can do is that you can average this object. So here's the idea. So if you take now a geodesic current, so I checked with the grandfather of geodesic currents here, that I could use the name geodesic current. So my geodesics, they are oriented, and the original definition is not oriented. So it's a little bit different, but I think he agrees, Francis Bonaon agrees with me defining that. So what is a geodesic current? It's just a locally finite and gamma invariant measure on G. So it turned out whenever you have such a current, nu, you can sort of average the length function. So the complication, it requires more work than what I just say. And then you obtain the length function for a geodesic current. Okay. Right, and these are functions which are way no algebraic in any ways. So now I'm going to introduce another class of function, and it's not just because I like complication, it's really because they happen in life, and I call them correlation functions. So you remember you have every geodesic give you a projector, and which is a trace one endomorphism. So what you can do now, if you have many geodesics, a finite configuration of geodesic, you can take the trace of the product. So So that's why they are called the correlation functions, because trace of projectors are correlation functions. Okay, so you know plenty of examples of these correlation functions. So for instance, if you take the case of SL2R, if you take two geodesics, so here I draw intersecting geodesic, but it's not at all relevant. So what is the correlation function of these two geodesics, of this configuration given by these two geodesics, is just related to the cross ratio of the endpoints of your geodesics. So the other example, which is also very important, is in SL3R. If you consider this type of configuration, you take a three geodesic, G1, G2, G3, and then you take the correlation function associated to G3, G2, G1. And this correlation function is called a Goncharov triple ratio, and it does play an important role in many things. So these functions, all these correlation functions, they are somehow Bayesian block to describe representation. For instance, you can use them to parameterize representation. That's the works of Falcon Goncharov and Bonin-Dreyer. And so these are very important functions. Right. But you can also average this object. And again, I'm going to average this object not just because I like complication, but because that's the way life is. So let's call this object a cyclic current. What is a cyclic current? It's just a gamma invariant measure on G to the n. So you take powers of your space of geodesics. Okay? You have to take a measure on that. And you assume, furthermore, that your measure is invariant by cyclic transformation. That is, if you, on G to the n, you have the action of the cyclic group. Just ask that. So that's reflect the fact that my correlation function, they just depend on the cyclic order of my geodesics. And then you just average that. So you take the average of a Gn mod gamma of such a quantity. So here I'm a bit sloppy, and you should notice that contrarily to geodesic currents, the fact that the action of gamma is now proper on powers of G to the n and powers of G, I mean, you have to delete diagonals of sort, right? So this tell you that there is no real dynamics associated to such a higher dimensional object, but they do play a role in this symplectic thing. So all these length functions, all these correlation functions, they are analytic, and that's essentially a result that was proved as a consequence of what we did with Bridgeman, Canary, and Sambarino. And so the first result is the following, that you actually have a formula that helps you compute what is the Poisson bracket of two correlation functions. Oh, I should say something. Yeah, there is this little sign, which means that I have to say something. So there is an important question, is whether these functions are defined or not, right? So sometimes they are not defined because your measure mu is too big, and so I'm just working under the assumption that we are in a situation where this formula makes sense. Okay, so you.
Is it zero in your two examples?
No, it's not zero.
By invariant.
No. Right, so here I mean, by what I mean that you want this quantity to be finite and well-defined, so you want to be, for instance, in this case, under the assumption that this function, Tg, this function of G, for a given row, or for a neighborhood in someone in row, this function is L1 with respect to mu. Okay, so there's lots of technical points about that, which are important, but I'm going to throw them under the carpet for now. Right, so here's the result, that you can take the bracket of two correlation functions associated to two different measures. These measures may be on different configuration spaces, meaning you have G to the n and G to the m, so it doesn't matter. And so the result that the corresponding object has the same kind of flavor. It is a correlation function. So here you have the product of that. This correlation function, which is related to a bracket on the space of a configurations. So I'm going to describe what is this combinatorial bracket and to explain to you that this formula makes sense. Don't something to say something more? No?
Maybe about n functions?
Oh, yeah, that's it. Thank you. So you will see later on that not only we can compute brackets of correlation functions with themselves, but we can also compute bracket of length function with length function and obtain a correlation function, and compute brackets of length function with correlation function and obtain another correlation function. That's going to be important with so, but this is simpler to state here, so I prefer that. Okay, so here is some application. So I'm going to give you 2 applications. So one of the application is it uses this notion of a representation, a projective representation, which admits a positive cross ratio. So what does this mean in this context? It just means that you say a representation admits a positive cross ratio if for any pairs of intersecting geodesic, then this number is between 0 and 1. Okay? And there are lots of examples of positive representation admitting, projective representation admitting that. So first I did that for one of the representation of a Hitchin representation for into SLNR, and then Giuseppe Martone and Tengrenjen did that for all the natural representations of a Hitchin representation. So all these objects have positive cross ratio. They also did it for Hermitian groups in those which are in SPN. That's right, yeah. And so when you have that, you suggest that it's true for all positive representation. In a recent work with Jonas Bayer, Olivier Guichard, Beatrice Pozzetti, and Anna Winart, we actually prove that for all positive representations, and I'm not going to define what it is, all the cross ratio that you can consider are positive. So that's a general right. So this is a notion which is not restricted to SL2R, right? So this is fairly general. But it's not true, of course, for representation in SL2C or whatnot. Okay. Right, so what is the result now? The result is that if you take a projective Anosov representation, that's which admit a positive cross ratio, then you have this convexity property. So it says that if you take a geodesic current which is supported on a geodesic lamination, and you take any another geodesic current, then this triple bracket is positive. So you may feel queasy about this triple bracket. So here is a very simple way to state that. Is that it means that if you take a Hamiltonian flow of your length functions, which comes from a geodesic current, geodesic lamination. So these are called in classical Teichmüller theory the earthquake path. No? How are they called? Hamiltonian flows of earthquake flow. Okay. So say that the second derivative, you restrict your length function to any of these orbits, then this function is convex. Okay, so you just say that. So that's a classical result, which is which was actually really our motivation. So in Teichmüller theory, this is a theorem of Kerckhoff, and it has been very useful. So that's was our motivation. So the second application is another proof. So we did that last week with De Canary. It's another proof of the Potry-Sambarino result. So what is the Potry-Sambarino result? This enlarging thing is pretty annoying. So this result is say that the entropy of simple roots on Hitchin representation is 1. So we all love this result. The proof is very clear and very understandable. So we have this new proof, which is very short, doesn't use even the definition of the entropy, but it's super confusing. So we are not totally sure it's a progress. But anyway, it's an application of the techniques of this paper. Right, so so these are two applications of the. So you really have to think that I'm going to explain the combinatorial thing. You really have to think that it gives you a tool to compute derivatives of functions. That's what we do in differential geometry, right? Compute derivative of functions and be able to do something about it. So a key object is what we call the ghost polygon. And this is going to be the start of the ghost jokes that I have prepared, right? So we even wanted to use a LaTeX package, which is called Halloween, in the paper, but maybe we stopped before. Okay, so what is a ghost polygon? So let's start with the configuration of geodesics. So you don't see the ghost polygon because it's a ghost. So what you only see is a visible edge of this ghost polygon. So what you do is you add some edges, and let's hope the color is going to do something. So you add an edge that goes from the ending edge of 1 to the starting edge of 2, and then you add the corresponding object, and now you obtain a true polygon, which is what we call the ghost polygon. And we have added this object, which we call the ghost edges, and which are very handy to describe the combinatorial structure. And now you have, remember that we work in an oriented setting. So this means that you have to orient your ghost edges. So now you have to remember that you're afraid of ghosts, so you run backwards. Okay? You are supposed to laugh at my jokes, right? Okay, so you start with a configuration of geodesics, and then you obtain a polygons, which is and then which has an even number of sides, and in the next you have a switch of orientation. Right. So so what next? Right. So when you have two polygons, you can define what we call the ghost intersection, and this ghost intersection is actually uses the representation that you have. So it is so this is you have this representation here. You have these two polygons, and so what is a ghost polygon? It's a very simple. It's look complicated, but in the end it's very simple. So right. So let's focus really on this part first. So you just take the sum of all edges, okay, whether they are ghost or visible, and you have to add the intersection number, algebraic intersection number of the two geodesics. Okay, so this intersection number, I should say that it's either 1. It should also be something like 0. So I'm or plus 1 or minus 1. No, I'm sorry, 0. But you also have to consider these objects, kind of objects, whenever you have a common endpoint. That's, you need to do that, unfortunately. And this is a kind of object that the intersection number has to be defined for as a 1/2. Okay, for this kind of object.
François?
Yeah?
Can I ask, so if in your ghost polynomial, in your ghost sites,
That's going to be ghost polynomial soon.
what happens if the two geodesic at the same endpoint?
Okay, that's what I said. That you have to define an intersection number which is 1/2.
No, but what's the ghost side? So if I start from a collection of geodesic, the slide before I thought.
If the 2 points, if there's no ghost edge between them.
Oh, right, okay. So if you start with a...
So if I start with a triangle as a...
Right. So if they have common, if the endpoint, yeah, that's right. So when the visible edge is what we call the phantom geodesic, the ghost edge then it actually, you have, because it's a product of projectures, it turns out that the correlation function is 0. Okay, but we actually have to deal with this fact in when it's not projective. I'm sorry, thank you. Right, so so here you add the intersection of these two edges, okay? Then you have to add the sign, and this sign is correct. So this sign, so when the two edges have the same status, this is +1, and when they have different status, this is -1. And then this is just, in that case, a cross ratio of the endpoints of the geodesics. And for some reason, we have to add the product of the correlation function with respect to rho, to h, and the correlation function with respect to g. So that's what we call the intersection number of two ghost polygons with respect to representations. Right, so the result is that actually this intersection number is just the integral of this intersection number. Right, it's just this formula, right? Okay, so I just need to explain to get the first result that that this I rho, this intersection of the two polygons with respect to rho, could be also think of as a correlation function with respect to some bracket of that. But that's, you can forget about this. Is going to be very formal. But you have to keep this formula in mind because this is the one that helps you doing computations. So the steps is first I want to understand what is the variation, what is the first derivative of your correlation functions. And actually this works in a fairly general context. You don't have to have a surface group. You can just take a hyperbolic group, and actually you don't have to have a group at all. That's what I'm going to explain. So that you have to do Anosov representation without groups. That's make life easier. And then we actually could compute the Hamiltonians of these correlation functions, and in the end we can compute what is the symplectic, what is the bracket, the symplectic product of these two objects. Right. So let's do this intermediate goal, which is to interpret this ghost intersection as a correlation function itself. So for that, we're going to use a trick, which is called the swapping bracket. So you start with a polynomial algebra which is generated by geodesics. It's just a formal thing. So objects in this algebra, they're just sum of maybe some coefficients. Maybe you want them over Q, and then you have formal products of geodesic. Okay, so this is just a polynomial algebra which is generated freely by generators, and these generators are geodesics. Okay. So it turned out that this, so this is a polynomial algebra, so it's a commutative algebra, right? And you want to turn that into a Poisson algebra. So there is a simple thing you can do, is you define the bracket of two generators as well, exactly this this quantity. So it first takes the intersection number of H and G, and then you take exactly the ghost edge that appear here, eta 0 and eta 1. Okay? And there is a theorem that says that this swapping bracket, which is defined on the purely formal object, actually satisfies the Jacobi identity. So it is and if it satisfies the Jacobi identity, it is exactly the definition of a Poisson algebra. So now, this is kind of a result when I came onto it, so it was either false or well known. So it turned out it was none. It was none of the above, right? So I have give you if you don't want to listen to the rest of the talk, I give you €5 if you find a proof of the Jacobi identity, which is simple because my proof is still 3-4 pages. So it's not very. I also tried to ask a computer to prove it, but it was a disaster. Right. So this is a Poisson algebra, and it actually related to many other things. So let's just think of it as the Poisson algebra for the moment. And it turned out that these ghost polygons themselves are related to this Poisson, to this swapping brackets. So what do? You take this configuration of polygons, G1, Gn. This is G1, Gn? Yeah, G1, Gn. And then you take the ghost edges. Okay, so you add the ghost edges, so you obtain something with a configuration of 2n geodesics. And then you take this formal product, this formal fraction, in the fractional algebra of the algebra I defined before, which is a product of the ghost edges divided by the product of the product of the ghost edges divided by the product of the visible edges. Okay. So every polygon gives you an element in this fraction algebra. And conversely, it's not very difficult that any fraction, well-defined fraction, is going to give you some polygons. So now this bracket between the two polygons is just precisely the swapping bracket of these polygons seen as element of the fraction algebra of the swapping bracket I defined before. And then you see that you can extend the correlation function. So you have defined it for polygons. So you just extend it by linearity to linear combination of polygons. And you can extend it by multiplication to products of polygons. And then you obtain exactly this kind of thing that the Poisson bracket, right, this intersection number is a correlation function of these two things. Okay? All right, so maybe I spend a little time trying to explain the proof of the theorem 1. How are you able to compute the Poisson bracket of these objects? And the first thing you would like to do is to understand what is the differential of your functions, of your correlation function. Okay, right. So it turned out that here, the fact that you have a discrete group is sort of irrelevant. And not only irrelevant, it also makes life more difficult. So, we are using a new trick, which we called a uniformly hyperbolic bundle. I'm going to explain it in a simple case. So you just take the as you know, the usual geodesic flow on the unit tangent bundle of H2, of the hyperbolic plane. You also take a vector bundle, which is defined over this unit tangent bundle, and maybe this bundle comes from the base, actually from H2. And then you have a flat, actually trivialized connection on E. And then the other object is a metric on E, right? And finally, you use the geodesic flow, you lift it by parallel transport to a flow on your vector space. So this is a classical construction. It's now classical of how you define Anosov representations. But it turned out that to do that, you don't have to have a surface group. You just need to have a flow. It's pretty. I mean, that's. I don't know. So anyway, so what is now a uniformly hyperbolic bundle? It means that you have a continuous splitting of your bundle into a line on a hyperplane. Okay, and you want that you have your contraction and contraction properties. It means that if you take a line, a vector in L, and a vector in V, if you take the image, the vector in the line grows much faster than the vector on B. So that's a domination property. It's a very classical thing again. So here, of course, this is related to Anosov representation, because in the Anosov representation, you consider the periodic case. You consider everything to be invariant under a group. And in that context, the metric G disappears, because all the metrics are the same. So you forget about G, and you just keep the first thing. But if you want to go to work on the universal bundle, you have to keep track of the metric. So a uniformly hyperbolic bundle is given over the geodesic flow. It's a bundle, a connection on a metric. Okay? And you need to have both. And because you have that, of course, you have a natural section of the space of endomorphism of the bundle, which is again this projector. You project on the line parallel to the hyperplane, and we call that a fundamental projector, and that plays the role of the projector I defined before. Right, this is a bounded section. Oh, I forgot something. You need to have, of course, some hypothesis, like phi t is bounded with respect to the metric. You have to have a classical bounded cocycle hypothesis that you need, for instance, for Lyapunov exponents. And right, so there is a little bit of hypotheses which are under the rug again, but it's not very important for the sequel. Right, so you have this bundle, and now what you want to do is, the first thing you want to do is, no, this we don't care about. Imagine that you have a family of universal hyperbolic bundle. So because they are all on the same bundle, and all these connections are trivial, you could use a gauge transform so that the connection is fixed. Okay, so now you want to say, okay, so I just vary the metric, and I want to understand what is the variation of my projectors. Because of course my projector, maybe the decomposition from my projector is not going to be uniformly hyperbolic with respect to the new metric, right? So you need to understand this projection, and how does this projector varies. And this is something which is classical in dynamics, and you have to solve what is called the cohomological equation. And the cohomological equation tells you exactly how does the fundamental projector varies. So it varies in the following way. So what is A prime? So A prime is just that you have this you have the variation of the metric. So because you have the variation of the metric, you can interpret the variation of the metric as an endomorphism. So that's going to be what you call your A prime. And you first take the commutator of A prime, and then you take this sort of complicated looking formula which is related to which is actually not very difficult. So, and what are G plus and G minus? You just pick a point on the geodesics, and this is not going to be dependent on the point of the geodesic, and then you integrate in the future. What do you integrate in the future? This quantity, okay, and you integrate in the past the quantity, this other quantity, and then you obtain a solution of the cohomological equation. So, which is maybe I shouldn't explain that, but. Right, but this is this is fairly simple. You obtain from the solution of the cohomological equation how do your projector varies in the general context. So now, now that you have that, you have to explain what is the relation between, right, so are you happy with that? You're happy because you remember that what you are doing is you're integrating the trace of product of projectors. So if you know how the projector varies, you know the differential of that, okay? So, but this situation seems to be a bit complicated because we have this, we have integrating on G plus and G minus, but it turned out that the combinatorics are magic. And there is again, some device that we call the ghost integration. So you start with a ghost polygon or a configuration of geodesic, and you want to integrate, again that, a one form. And to make it simpler, in that case, I'm going to take a one form, which is an element, a one form with value in the endomorphism. And I want this one form to be L1 along geodesics. And also I want this object to be closed, and which means that if you integrate on 3 geodesics, it's going to be 0, right? You need to have some condition like that. So then what is the ghost integration of your one form with respect to your polygon? It's just you integrate over all edges, but ghost edges and visible edges, and that's your ghost integration. Okay, so what's the relation with that? Right, so sorry, here I should say that here I'm using the fact that you have a surface, but there is a definition of a ghost integration that doesn't use the fact that you have a surface. So again, in a fairly general setting. So what is the result? That you can actually compute the variation of your correlation function as this ghost integration thing. So that's an important fact. Oh, right. And what do I wanted to say? All right, so then once you know the derivative of the function, then you compute the Hamiltonian. You're smart enough to find out what is Hamiltonian and everything, and you can push. It's just combinatorics you have to be careful at some point, because again I put under the rug a whole lot of regularity issues, and really at some point we have to deal with Fubini theorem. So your functions are better be L1. So you have to check some things are L1. So there are some technical stuff which are important. Okay, so is there any question to this part? So all clear? Why are you smiling? Why are you laughing? Okay. Okay, so you have to remember what's a ghost polygon is, right? Mm. Do you want to have comments on a uniformly hyperbolic bundle?
Yes.
Okay.
I don't like the name.
Oh my God. I'm not going to call them a Anosov hyperbolic bundle again, right?
That's a dominated splitting.
Dominating was really on compact object, right?
Yes, but one being faster than the other is a dominated property. It's not a uniform property.
Yeah, but the point here is that you have to think of this object as not only a bundle on a connection, but also as a metric. That's a thing that helps you. So for instance, it should connect with classical differential geometry. So there is this result of Uhlenbeck is if you take in the hyperbolic 3 space, if you take a quasi-symmetric circle, but with a constant which is very close to 1. So then there is a unique minimal surface for that. But a minimal surface, if you think about it, is defining you a metric on this bundle. So some of the question is to understand this kind of a situation when you have this differential geometric object, it's a Higgs bundle or whatnot. When does it give rise to a uniformly hyperbolic bundle? So my guess is that this appears in many situations, and so this kind of solutions of so for instance in the maximal surface case, you really obtain again a uniformly hyperbolic bundle. So this is something that connects a lot with differential geometry and analysis of geometric analysis of minimal surfaces or maximal surfaces. Okay. So again, I want you to remember that you can compute the variation of the projector using the cohomological equation. And if you don't know the cohomological equation, you have to read it as soon as you leave this room. Right. So, okay, I have 10 minutes. That's it? Okay. So maybe I'll explain how do you go to the convexity of length functions. So it turned out that to integrate the length function into the picture, you need to take your swapping algebra, which is differentiated by this geodesic, and you need to have new generators. And these generators are we call them LG. You have to think of them as logs of geodesics, whatever this means. But this actually means that the only thing you need to understand is what is the bracket of this with the other generators. So the bracket of LG of my new generator with that is just going to be the bracket of G on H, where G is a classical geodesic, but divided by G. So it's really like taking some logs, derivative. So what is now the derivatives? You need to understand what is the bracket of two of your generators, and the bracket of two of your generators is going to give you by the intersection the bracket of G of H. No, actually, if I use a bracket here, I mean the configuration of the geodesic given by G on H, and then you have to divide by G times H. So you have to add to your swapping algebra new generators, which we call LG. And when you have these generators, you have a similar formula that helps you understand the brackets of correlation functions and length functions, and brackets of length function. I'm pretty sure my formula is not correct because I forgot the dimension term. Yeah, I'm sorry. So this formula is not correct. Sorry about that. Yeah, so formally we have to add, anyway, let's not talk about that. So, so now that you are able to combinatorially construct things, you actually are able to obtain a formula for this triple bracket. And this formula for this triple bracket is just the integral over this object. So you take some special configuration of geodesics. You put epsilon 0 on epsilon 1. So what is epsilon 0? It's the intersection of G0 on H, and epsilon 1 is the intersection between G1 and H. And you have to integrate this quantity, because that's really a result of your computation. And you have to integrate under that. So what is this space of configuration that you consider? So remember that G0, G1 and G0, they are in the support of your geodesic lamination, so they never intersect. So that's why this formula is a little simple. And so what is this configuration of geodesic that you consider? You just consider those geodesic. You have G1, G0. You on H intersect G1 before G0. Okay, so I just care about in this picture about the orientation on H, but G0 could be and G1 could be oriented this way or oriented this way. Okay, and right. So this is just done by again using this this tool of this combinatorial tool, which really came as a surprise. And now what you're only left to do is to consider this configuration and show that this integrand is positive. And this is, well, this is some exercise again. Not totally easy, but whenever you have this configuration, this quantity is positive. So this certainly means more than it says, but that's the way it is. And okay, that's the end. So I should stop now.
Question? Question about the entropy?
So you said you can compute the Hamiltonian vector field for correlation functions?
Yes.
Can you also compute the Hamiltonian flow?
That depends what you mean by computing, right?
Can you write down the path of representations if I start at one?
No, but here's something that we can do, for instance. We also made this computation last week. We can obtain some complicated integral formula. You can write what is the pressure length of a Dehn twist using some integral formula. But it's not, well, that depends what you mean by computing. Maybe if you can plug that into a computer and ask him to compute. This could be true, right? But it gives a formula for the pressure length of a Dehn twist, for instance. And this formula could be computable by at least by a computer.
Just a very nice question about Kerckhoff theorem. Is it this version where you explain that you can use earthquakes, finite number of earthquakes, to go from one point to the other? Can you prove the same thing?
Okay, so that's really one of my favorite questions, actually. So it was a question that was asked to me by Mariam Mizahani a long time ago. So you have this earthquake theorem. And this earthquake theorem is because you have these nice functions, which are this length function of geodesic lamination, and they have this convexity property. Okay, so we proved here that we have this kind of function which has this convexity property, but they are not enough to go from one point to another by some earthquake flow. Okay. So
should it be true with earthquakes with bulging?
Maybe, but the point is that you have to find what are the generalization of this earthquake flow. Are there other functions which are convex, so that the length functions are convex under the Hamiltonian flows of these functions? And I would dream yes, but all the computations so far we did with Martin Bridgeman had been inconclusive. But that's really a hope. I mean, for Hitchin representation, of course. But we are able. So that's another application which I didn't talk about. That if you have a geodesic lamination, then you have all these triangles and all this length function, and all this give you commuting functions, for instance.
So you can thank the speaker.
No, that's your job now. No, sorry.